Hello students, welcome back. In the previous videos, we did some computations. We did some theory, yes, but mostly we did computations. First, we went through eigenvectors and eigenvalues for 3 by 3. And then we went through something for, 4 by 4. It turned out you can set up the characteristic equation. Yeah, same matrix except for negative t, minus t in principal diagonal. Everything else remains the same. And take the determinant, set it equal to 0, and simplify, and you're going to get the solutions. T equals to 0, 1, and 2, and another 2. Those are the eigenvalues. Now, based upon these eigenvalues, we can find out eigenvectors. We did the simplest case, lambda equals to 0, we did it. The second case, I'm going to leave to students. Now let's do the hardest case. Why is this hardest? That's because of the duplicate, of course. Let's set up. So this matrix times the second matrix, column vector rather, is equal to twice of this column vector. So let's work this one out based upon these two. Okay, all right. So what do we have here? Negative 4x minus 2y plus 0z minus 2w. That's equals to 2x. Next, 6x plus 4y plus 0z plus 2w is equal to 2y. Next, minus 6x minus 2y plus z minus 3w is equal to 2z. And then finally this, 6x plus 2y plus 0z plus 4w is equal to 2w. Is everything correct here? Okay, all right. Okay, a little bit of simplification here. Flip everything to the left-hand side, subtract by 2x, so negative 6x, and then this is going to down to 0. Subtract 2y, so that's 2y, that goes down to 0. Subtract 2z, so this is negative z, and this is 0, and then subtract 2w, and that goes down to 0. Is everything correct so far? Okay, all right. Some further simplification. How about some division here? Let's see. First line, all even, so divide by 2. Okay, sorry about the previous typo. I corrected everything. Second row, again, divide by 2. So 1 and 1w. Here, I can't really do too much. How about this one? Yes, I can do that. All even, so divide by 2. Okay, all right. Looks good. and then some further simplification. What can we do here? First row and second row, they are identical, aren't they? So if I add the second row to the first, what do I get? That goes down to 0. That 2 goes down to 0 or 0, right? Add up, so we get 0 equal to 0. So first row gave me nothing. Now how about the fourth row? Subtract, again they're the same, so that gives me nothing. So what do I have? I have the second row and third row only. Make sense? Okay, so far what do we have? We have 2 equations and 4 unknowns. Is it going well? Yes, actually it is going well, because we have duplicate here. Okay, and then what do we do next? What shall I eliminate here? If I multiply 2, I'm gonna get, no, I did a bit too much already, so let's take an extra step and do it. Multiply by 2, then 6x, 2y, 2w, and let's add this one to the third line here. 6x, 6x, that's gonna be gone. And 2y, 2y, that's gonna be gone. And z, that's okay. 2w minus 3w, so I'm gonna get z minus w. Okay, alright. So we get negative z minus w is equal to 0. So if I flip z to the other side, w to the other side either, z is equal to w, negative w, I can't do this very well. Negative z is equal to w. So z equals negative w, okay. Let's solve everything with respect to w. Okay, alright. We got that. And plug it into the second line. 6x plus 2y plus 2w equal to 0, and let me see. Here we already used up. See, so let's solve it for w. So 3x plus y plus w, so w is equal to negative 3x minus y. Are you with me here? Okay, alright. I need 2 characters. Looks like x and y will do the job. So w is negative 3x minus y. Z is equal to negative w, so it's 3x plus y. Does it make sense? So this is what I got from the third line. And then plug into second line with a bit of simplification. All even, so divide by 2 and simplify. And plug in w equals to, solve for w, negative 3x minus y. So z is negative of that, so 3x plus y. So are we all set? Oh yes. We get x equals to 1, y equals to 0. So 1, 0. And let's see, x is 1, y equals to 0, so this is negative 3. No, z first. Positive 3, negative 3. We get this time putting x equals to 0 and y equals to 1, I'm gonna get x, y, z, w is equal to 0, 1, and then let's see, z is 1 and w is negative 1. So we have two eigenvectors, 1, 0, 3, negative 3, and 0, 1, 1, negative 1 from these two duplicate eigenvalues. Eigenvalue lambda equals to 2 is duplicate. So it's not a surprise that we ended up with two eigenvectors associated to the same eigenvalue. It's not a surprise. And why did I plug in 1 and 0? I could have plugged in 1, 1, 1, negative 1. I could have plugged in various. It's just that 1 and 0 and 0 and 1 were the simplest I could think of. Do not get 0, 0. If you plug in all 0, then you get all 0. And that's the only thing that you have to remove. Otherwise, it's all okay. So 1 and the other 0, that's the simplest case, usually. Let's see, do we have enough time to check? Okay, let me stop this recording here and write some program here. Okay, welcome back, students. I completed writing the Mathematica program here. It's not a program, just some coding. Anyway, the matrix I'm looking for is this matrix. Let me copy and paste it over here. And then you can define it using Mathematica command by each row. Each row, negative 4, negative 2, 0, negative 2, 6, 4, 0, 2, and so on. Each row. And then you can check the matrix form by this command, matrix form, bracket of A, and this is what it spits out, and please check. And how about eigenvectors V and W? 1, 0, 3, negative 3, 0, 1, 1, negative 1, but they should be column vectors, so I wrote them as columns. So each row has only one number, so another brace here, 1, 0, 3, negative 3, kind of like this. This is the way you write the column vectors in Mathematica. And then you can check those. Matrix form for V, matrix form for W. Okay, they check out. And then let's check the matrix form for AV minus 2V. So we need this dot for matrix multiplication. AV minus 2V is 0. AW minus 2W, again, 0 matrix. So yes, AV and 2V are the same. AW and 2W are the same. So that actually satisfies as the checking process. So we know we did everything correctly. And let's go back. So what do we want? We want eigenvectors for these two eigenvalues, duplicate. So we have A times xyzw is equal to 2 times that. And then we are simply solving the system of linear equations. So far so good. And then a bunch of elimination. Simplify some coefficients first. And then adding to another row and things like those. We got 0, 0, and 2 rows disappeared. So we lost 2 degrees of freedom. So we're going to get 2, out of 4 characters, lost 2 degrees of freedom. The other 2 will be determined. So we have 2 characters flying around, and then the other 2 will be determined. If only one disappears into trivial equation, then we have 1 freedom, and then the other 3 will be determined. And then just technical computation, systems of linear equation. Everybody knows that. Just some substitution, plugging in. And then we got z and w written in terms of x and y. So plugging in x equal to 0 and y equals to 1 and vice versa, x equals 1 and y equals to 0, we get eigenvectors. I could have selected other problems like x equals to negative 17 and y equals to square root of 2. You could have done that, but why would anybody do that? Take the simplest numbers, 1, 0, 0, 1, and those are eigenvectors. Okay, that's how you get eigenvectors if you know eigenvalues. How do you find eigenvalues? They are coming from solving characteristic equations. These tend to be really long, so in the exam, please expect some long problem with some multiple parts. Do you have time for the next problem here, eigenspace? Okay, let's talk about it. We'll probably have to talk about these again in separate video. Let V be a vector space and let L be a linear operator there. Then the set of all eigenvectors form a subspace, and we're going to call that eigenspace. Okay, we have to prove this is a subspace. Oh, all right, I'll have to prove to the readers. So probably this is a homework problem then. Okay, set of all eigenvalues is called eigenspace. So you're gonna get, let's get the previous problem. Okay, for this matrix, or the linear operator defined by this matrix, okay, we don't need that. Okay, all right. So let's go back to this. This is a 4x4 matrix, so it defines a linear operator from R4 to R4, and these are the eigenvalues. For each eigenvalue, you're going to have the set of all eigenvectors associated with that particular eigenvalue, and that is called an eigenspace. For example, we went through an eigenvector for lambda equal to 0 in the previous video, and get them all, then you're going to get one-dimensional eigenspace. Earlier in this video, we went through these two. And then we ended up with finding two eigenvectors here. And it is not going to be too difficult to prove that those two are linearly independent, as a matter of fact. Detail is left to the students. And we end up with a two-dimensional eigenspace. I could have found eigenvector for this one and then determine an eigenspace for lambda equals to 1 as well. In any case, all these are called eigenspace. And the proof, those form a subspace, that's left to the students. How about the next statement here? Let v1, v2, v3 all the way over to vn be eigenvectors of L with eigenvalues eigenvalue lambda. Okay, they all share the same eigenvalue, all right? Like this case, we had two linearly independent vectors that share the same eigenvalue, all right? Then every non-zero vector of the span is an eigenvector. Okay, the linear combination of all these is an eigenvector of the same eigenvalue as well. Looks like it's not too difficult to prove either, so I'll leave that to students.